Hello everyone, my name is Neng Huang. Today I'm going to talk about the approximability of presidential type predicates. This is a joint work with Aaron Petechin. In this talk, I will first introduce the notions of predicates and approximability, and then I will discuss a few techniques in designing approximation algorithms. And finally, I will briefly sketch the proof of our result. So first of all, a Boolean predicate P of arity k is a function that maps an element from -1, 1 to the k to -1, 1. A presidential type predicate, which is the topic of this talk, is a Boolean predicate of the form sine of a times x1 plus x2 plus ... plus xk. Here we assume that a is a natural number, and this linear sum is never zero for every input x. We can view the presidential type predicate as a vote, where x1, the president, has a vote of weight A, and x2 to xk, the citizens, have the votes which are of the same weight 1. We remark that this is a special case of balanced linear threshold function, where every variable can have a different weight. A few examples. When a is equal to k minus 2, this is known as the monarchy function. In the monarchy function, x1, the monarch, has weight k minus 2, and the monarch gets their way unless all the citizens x2 to xk unite against the monarch. The second example is when k equals 1. This is the well-known majority function. Having defined predicates, let's define CSPs. An instance of constraint satisfaction problem is specified by a set of variables which take values in some finite domain D, and D in our case is simply -1, 1, and a set of constraints where each constraint is a predicate applied to a subset of variables. Given an assignment to the variables, the constraint is said to be satisfied if it evaluates to 1. The goal of the CSP is to find an assignment that satisfies as many constraints as possible. In this talk, we will only consider CSPs whose constraints are of the same form. That is, they're defined by the same Boolean predicate P applied to a subset of variables or negated variables. Let CSP of P be the set of such instances. The canonical example is the 3 satisfiability problem, where we have a set of Boolean variables and a constraint is the OR of 3 variables or negated variables. A trivial algorithm for 3-set is to assign the variables uniformly at random. This algorithm, simple as it is, satisfies 7/8 fraction of constraints in expectation. And a natural question is, can we do better than this? And the answer is no. Hastad showed that even if the given instance is perfectly satisfiable, it is still might be hard to do better than 7/8. This leads us to the notion of approximability and approximation resistance. We say that a Boolean predicate P is approximable. If given a nearly satisfiable instance of CSP of P, we can find an assignment that satisfies Rp plus some constant fraction of constraints, where Rp is the probability that a constraint is satisfied by a random assignment. Otherwise, we say P is approximation resistant. So essentially, in this definition, we want to beat the random assignment, which satisfies an Rp fraction of constraints. There is a rich body of work in this area. On the algorithmic side, we know that max cut is approximable, and also majority function and monarchy function, which are both examples of presidential type predicates, they're also known to be approximable. On the hardness side, Hastad showed that 3-set and 3 XOR are approximation resistant. Petechin showed that there is a certain balanced linear threshold function that is approximation resistant under the unique games conjecture. There have also been several criteria for approximation resistance. Our result is the following. We showed that if A the weight of the president is at least some constant times k, then the presidential type predicate is approximable for a sufficiently large k. Our result filled in a huge gap between what was previously known about presidential type predicates. So previously, we know that monarchy predicate, where A equals k minus 2, is approximable, and also almost monarchy predicate, where A equals k minus 4, is approximable. For smaller a's, Hast showed that predicates close to majority are approximable, and his result implies that when A is big O of square root of k, the presidential type predicate is approximable. Now let's discuss a few techniques to design approximation algorithms in order to show that a predicate is approximable. So our approximation algorithm will consist of two steps. We first solve Raghavendra's semi-definite programming relaxation on the given CSP instance, which will produce a set of biases and pairwise biases. And then we need to come up with rounding schemes which take these biases and pairwise biases as inputs and output an integral solution to the original CSP instance. Let's first look at Raghavendra's canonical SDP relaxation. The idea behind this SDP relaxation is to search for a set of global biases and pairwise biases. And the intended meaning of the bias is BIs. The BI is intended to mean the expected value of xi, and Bij, the pairwise bias, is intended to mean expected value of xi times xj. And then for each constraint Ci, the SDP locally searches for a distribution of assignments which agrees with the global biases and pairwise biases and maximizes the probability that this clause is satisfied. The objective of the SDP is to maximize the sum of the PIs. Raghavendra showed that the integrality gap of this SDP is essentially equivalent to the unique games hardness of the CSP. So if the unique games conjecture is true, then this is the best SDP relaxation we have. For us, it is more important to understand what kind of biases and pairwise biases this SDP gives us. For this matter, we define the KTW Polytope. Given x in -1, 1 to the k, let v of x be the vector obtained by concatenating x with its pairwise products. And for a Boolean predicate p, we define its KTW Polytope to be the convex hull of Vx, where x is a satisfying assignment of p. So if the SDP thinks a clause is satisfied, then it will, for that clause, obtain a distribution of satisfying assignments, and the biases and pairwise biases of that will be a convex combination of the assignments, which means it's in the KTW Polytope. Kot, Tusiani, and Wara, who studied the KTW Polytope, showed that if there exists a vanishing measure on the polytope, then P is strongly approximation resistant. Here, strong approximation resistance means that we cannot even deviate from random. We can neither do better nor do worse than a random assignment. Now let's design the rounding scheme. Let P be a presidential type predicate that we want to approximate. Our rounding scheme will be symmetric under permutation of indices so that it looks the same locally from every constraint. This means that it suffices to show that our rounding schemes achieves a positive values on a single constraint of the form P. Note again that if the constraint is satisfied, then SDP will return a point from the KTW Polytope. And this implies that A times B1 plus B2 plus plus BK is greater than or equal to 1. And this is because every solution X satisfies A times X1 plus X2 plus plus XK is greater than or equal to 1. Recall that we have assumed that A is a natural number. And this linear sum is a positive value. How do we associate it with expected value of P? And the answer is use discrete Fourier analysis. So the Fourier expansion of a Boolean function f is given by a sum of f hat sub s times chi sub s times x times chi sub s of x, where s ranges from all subsets of integers from 1 to k. Here, f hat sub s is called the Fourier coefficients of s on the set S and can be computed by the formula expected value of f times chi sub s. And chi sub s is simply the monomial, the product of xi's, where I is from the set S. A simple example, the majority function on 3 variables has the Fourier expansion x1 plus x2 plus x3 minus x1 times x2 times x3, and entire thing divided by 2. We have the following simple proposition on the Fourier coefficients for odd functions. So if f is an odd function and s is a subset with even size, then f hat sub s is equal to 0. And the proof is simple. Since the set S is of even size, we know that chi sub s is an even function, and hence f times chi sub s is an odd function, which implies that f hat sub s being defined by the expected value of f times chi sub s is equal to 0. Since presidential type predicates are odd, we can apply this proposition to presidential type predicates. So let P be a presidential type predicate. By linearity of expectation, expected value of P is equal to the expected value of its Fourier expansion, which is in turn equal to the sum of P hat sub S times the expected value of the monomials, where S is an odd subset of the integers between 1 and k. Here, P hat sub S is a constant defined by the predicate, while the expected value of the monomial is determined by our rounding scheme. Let's look at a simple example, majority on 3 variables. Recall that it has the Fourier expansion x1 plus x2 plus x3 minus x1 times x2 times x3 divided by 2. And by linearity of expectation, the expected value of this predicate is equal to 1/2 times the expected value of x1 plus the expected value of x2 plus expected value of x3 minus expected value of x1 times x2 times x3. Let epsilon be a small constant that we determine later. Consider the following rounding scheme. For every I, we independently pick xi equals 1 with probability 1 plus epsilon bi divided by 2, and xi equals -1 with probability 1 minus epsilon bi divided by 2. Then the expected value of xi is equal to epsilon times bi, and the expected value of x1, x2, x3 will be epsilon to the third, b1, b2, b3. Then the expected value of our rounding scheme will be epsilon times b1 plus b2 plus b3 minus epsilon to the third, b1, b2, b3, and the entire thing divided by 2. Recall that if these biases are from the KTW Polytope, then we have b1 plus b2 plus b3 is at least 1. So by choosing a small enough epsilon, the degree 3 term can be made arbitrarily small compared to the degree 1 term, and we will have a positive value for the expected value of px. The essence of this rounding scheme is choosing the expected value of the monomials such that the expected value of our rounding scheme approximates a multiple of the linear sum, which is positive. The question is, what kind of freedom do we have in choosing these expected values for the monomials? So it turns out that we have a fair degree of freedom in doing so. It is known that for every odd a in functions fa, which takes biases and pairwise biases of a variables as inputs and output a number between -1, 1, if fa is continuous and is symmetric, then there exists a rounding scheme such that the expected value of chi sub s of x can be made to be approximately equal to a multiple of fa. So what are the symmetric requirements for fa? So first, it has to be invariant under the permutations of indices in S. And second, for every I in S, if we flip the variable xi, then the expected value of the monomial should also be flipped. A few examples, we can take f1 to be any continuous function such that f1 of bi is equal to minus f1 of minus bi. So f1 should be odd function. And we can take f2 to be any continuous function such that f2 of bi, bj, bij is equal to f2 of bj, bi, bij. So this corresponds to permuting I and j, and it should be also equal to minus f2 of minus bi, bj, minus bij. And this corresponds to flipping the variable xi. Now let me briefly sketch the proof of our result. We will only sketch the special case where the weight of the president is equal to k minus 2c. So as a first attempt, let's try the rounding function which we used for the majority predicate. Let alpha be b1, which is the bias of the president, and beta be the sum of the biases of the citizens. Then we know that k minus 2c times alpha plus beta is at least 1. Let p hat sub p be the Fourier coefficient of the president, p hat sub c be the Fourier coefficient for a citizen. If we let the respective value of xi be epsilon times bi as before, then the degree 1 terms in the Fourier expansion is epsilon times p hat sub p times alpha plus p hat sub c times beta. It would be great if p hat sub p is equal to k minus 2c times p hat sub c, because if this were the case, then the degree 1 terms will be positive. But in reality, p hat sub p is exponentially larger than p hat sub c. But don't worry, let's use the higher degree terms to get more beta. Define S to be the biases, the pairwise biases of the citizens, and consider the following approximations. For degree 3 terms, let's consider the sum of bi1 times bi2i3 plus bi2 times bi1i3 plus bi3 times bi1i2. And this sum is approximately equal to beta times S. And similarly, we can make the degree 5 terms be approximately equal to beta times x squared, and degree 7 terms beta times s cubed. So we could potentially use these terms to counteract the excess alpha if we can get rid of s. Intuitively, the worst accepting assignments are when this linear sum is exactly 0. So the vote passes with a margin of exactly 1. Let E be the average of S in these worst cases, and write S equal to E times 1 plus delta. So delta here will be a parameter that characterizes how far we are from the worst accepting assignments. And the previous approximations will become the following. We'll have beta times E times 1 plus delta, beta times E squared times 1 plus delta squared, and so on. And since E is a constant, we can shift them to the left-hand side. So we have two cases on delta. If the absolute value of delta is small, then all of the previous expressions are close to a multiple of beta and can be used to counteract the extra alpha. If delta is large, then the degree 1 terms are actually very favorable for us, which will also give us a positive value. Note that by taking a linear combination of beta times 1 plus delta, beta times 1 plus delta squared, we can get beta times h of 1 plus delta for any polynomial h without a constant term. So we want h to be close to 1 when delta is, the absolute value of delta is small. And there are a few technical requirements for h. We want h1 to be 1, and the derivative of h, the derivative and second derivative of h at 1 are both 0. We call such polynomials h rounding polynomials. So for the special case, we actually showed that h1 plus delta equal to 1 plus delta to the third works. And here is a figure for this polynomial. And note that when delta is close to 0, we actually have a multiple of beta that is close to 1. And this is our final rounding scheme. For xi, we will round it as usual. It will have bias some constant times pi. And for higher order terms, we will use the previous approximations. And their coefficients will be determined by the rounding polynomial. So this rounding scheme, we showed that this rounding scheme has a positive expected value, and this implies our theorem. In conclusion, so we showed that these predicates are approximable, but our analysis actually only works when k is sufficiently large. So a problem is, can we prove for every k? We showed that we can do a tiny amount better than random, but what is the best amount we can do? Moving on to general balanced LTFs. In the introduction part, we know that there is a balanced LTF that is shown to be approximation resistant under the Unigame's conjecture. So where is the boundary between approximability and approximation resistance? Can we give a decidable characterization for balanced LTFs? This is the end of my talk. Thank you for your attention.